Hi, I'm just Koros, and I'll be talking to you about my project constraining in-gamma cross-sections via surrogate measurements with Hyperion. So first, let's take a look at the motivation behind this project. We're interested in neutron capture cross-sections because these are important for understanding any nuclear reaction process where photodisintegrations or neutron captures play an important role. And we use the surrogate method and other indirect reaction methods in situations where, for some reason, the reaction that we're interested in is not accessible to perform in the laboratory. So for this experiment, we have chosen 64 and 70 zinc targets, and these medium mass isotopes will allow us to approach our calculations both from the Hauser-Feshbach statistical continuum as well as from the discrete states shell model approach. Next, let's take a look at Hyperion itself. Hyperion is a particle gamma detector array. So it consists of up to 14 high purity germanium clovers, which are surrounded by BGOs for quantum suppression. Then inside the target chamber there in the middle, we have a silicon telescope for particle detection. So all of this together allows us to detect particle gamma coincidences, which is important for selecting our compound nucleus of interest, so we know exactly what reaction we're looking at. Next we'll look at the surrogate method. So the basic idea of the surrogate method is that we are using some surrogate reaction to populate our compound nucleus of interest. So the formation probability of the compound nucleus via either reaction can be calculated using optical model potentials. And then the experimental quantity that we're interested in here is the gamma decay probability. So what is the probability that this compound nucleus we've created will de-excite via gamma emission? And we can use this experimental quantity to feed back into our calculations for the desired reaction in order to constrain those n-gamma cross-sections. And the reason we can't just get an exact number is because the different reactions populate these compound nuclei with different spin distributions. So we have to correct for that in our calculations as well. So this is some samarium data that was taken with Starlighter, the predecessor to Hyperion, in 2015. It's available for surrogate analysis, so I've been developing my method with this. And I'll use it to show you the basic analysis process in order to obtain those gamma decay probabilities. So all of this data is for the 152 samarium PT reaction. So the compound nucleus that we're looking at is 150 samarium. And we've gated on triton. So here at the bottom right, we have the triton particle spectra. At those lower energies, we can see discrete states, and at the higher energies into the continuum, as we expect. And so this is the denominator of our equation here. We also have some efficiency of gamma detection as a function of gamma energy in the denominator as well. And so on the top right here, we have a gamma spectrum that's gated on the tritons. So this gives us the number of particle gamma coincidences for the numerator of our equation here. And I've gated this above and below the neutron separation energy, because above the neutron separation energy, neutron evaporation becomes available. And then we're seeing gamma emission from 149 samarium as well. And here on the left, we have the resulting gamma decay probability for this particular gamma energy. And you can see above that neutron separation energy, our gamma emission probability drops off, as we would expect as that neutron evaporation channel opens up. So these decay probabilities are the experimental quantity that we then feed back into our Hauser-Feshbach calculations that allows us to constrain the neutron capture cross-sections. So this project, currently we've completed the zinc campaign at Texas A&M last November, and I'm currently working on sorting and calibration of that data. Next steps will be extracting the gamma decay probabilities from there, and then going on to the Hauser-Feshbach calculations to constrain those cross-sections as well as a little bit of exploratory work into the surrogate method. And thank you for your time. That's all.